Hello class, welcome to today's lecture, Units and the Metric System, with the overall topic of communicating the world to each other. So the topics for this lecture are just two. We're going to be talking about units and the metric system, but the metric system has a couple of subtopics we need to cover, which are the 7 base units of the metric system, using prefixes, and combining units to describe more complicated systems of measurement. So to start, we'll talk about units and their importance. So here we have an image of the allegory of the cave, which describes how one man chained to a wall cannot really truly experience the world, so he sees it through however the second guy is showing it to him. In this case, he is seeing a bird reflected on the wall off of sunlight. This is a philosophical topic, but what I think is interesting is that it does still it still applies in chemistry. So if you think about it, the way we communicate to each other really affects the way other people understand what we're talking about. This is important because in chemistry, if we are not precise and succinct in how we talk, we can cause confusion, which can cause problems. So all that said, what's a unit? So a unit is a simple descriptor explaining what you are looking at or working on or describing. So to illustrate the importance of this, I am going to invoke two of the US's top scientists. For example, one. So for this example, we are referring to Dr. Ion, who has a PhD in analytical chemistry, and Dr. Isotope, who has a PhD in biochemistry. In this example, a lot of fish, Dr. Ion went to the aquarium with his family last weekend where he saw the following tank. So you see, he's looking at it right here, right now. So the next day, he goes back to work and he's talking to his colleagues. And at this day, he goes and talks to Dr. Isotope and he tells her, hey, I saw a lot of fish this weekend. This allows her to think about what he said, right? So she's thinking, it calculates in her head, and she imagines a lot of fish. 15 fish right here, all of them of different types. The problem here is that because he was not precise in how he described it, she did not imagine what he wanted to describe. So instead, to be more precise, he can say, he can modify his unit and use more of them to describe what he wants to focus on. So instead he says, I saw one whale shark, a school of green fish, and amongst many other species. In this case, other species is itself a unit. So now he's broken down a statement and now he has 3 different things he's describing, all of which have their own unit. He saw one whale shark, one single whale shark, a school of green fish, which is a group of fish, which is itself defined, and many other species. So now he said there are multiple other types of fish. So now she gets to imagine, and she might not get everything, but she might catch this, she might catch this, and she might catch all these. It is an interesting way that he can define what she thinks about and focus what he wants her to see, because he wants her to understand his lived experience. So what he did is he was more precise so that she could hear it. In this case, Dr. Isotope was more closely able to imagine the things that Dr. Ion wanted her to understand. So the takeaway is that the way we describe the world directly affects how other people understand it. Example 2. I look at this elephant and I can say this elephant weighs a lot. In this case, lot is a unit that means big, right? It's kind of undefined, but a lot. I tell you a lot, you know what a lot is. I can, however, instead say 3 to 7 tons. We know that a ton is big, so saying it's 3 to 7 makes that this creature is really big. We can also describe this creature as being 5,000 to 14,000 pounds, which is in the opposite direction. We are describing a lot of smaller units. So in this case, instead of thinking about it as a little bit of big things, we think about a lot of little things. They both describe the same creature, this elephant, but now we are describing them differently. The takeaway here is that there are multiple ways to describe the same thing. Tons is a big measurement and it makes us think of big things. Pounds is a smaller measurement, which makes us think of smaller things, which is why we need a lot of them. If you told me that it's 5,000 pounds, I know that I weigh about 200. So in order for there to be 1,000 pounds, there would need to be 5 of me. And in order for all of us to be as big as an elephant, there would need to be 5 times 5, 25 different me's to be as big as one elephant. And I think about it that way because I've had these things described. I know about how big a pound is. I know about how big a ton is. Example 3. In this case, we have 3 cartons. I can say I have a lot of eggs, big quantity, right? I can also say I have 36 eggs. I could count each individual egg. I can also say I have 3 cartons of eggs. This one could be complicated because in other grocery stores, a carton might not have 12, but in this case, it describes 12. Which lastly, we can say that I have 3 dozen eggs. The takeaway that I want you to think about is that just as before, you can define things depending on what we have, but the bigger thing here to catch is that the word dozen. You already knew what a dozen meant. Why? Because your whole life, you've been told what a dozen is. You can order a dozen donuts, a dozen eggs, a dozen bagels. You know that when you order that word, you will get 12. There is a defined social descriptor here that we all agree to. Last example, which is what happens when you don't have a unit. Here you can have a conversation with a European and a United States person. The United States person can say, I need you to travel 100. The European will immediately say 100 what? Kilometers, miles, feet. If you don't tell me what the unit is, I don't have a reference of what you mean in the real world. I can try my best, but I will not match what you're trying to tell me unless I specifically have the unit you describe. This is important because conflicts of description can cause problems. One of the biggest issues in science before modern times was that different people would have different ways to measure units. So if you were talking between a French person and an English person, for example, if you said something was 1 inch long, those things would be different lengths. A more recent, more serious one was the Mars Climate Orbiter. This was supposed to be an orbiter that would fly around Mars and make sure that we got good data out of it. We launched it from Earth on December 11th, 1998. 9 months later, it arrives on Mars and we lose contact with it. We never found it again. The reason we lost track of it was because the thrusters, which it uses to fly around, needed to be described in Newton seconds for the software, but the thrusters had a different software which reported numbers in pound force, which is an imperial unit. Imperial being what Americans use, and Newton seconds being the metric system, which is what the world uses. This ended up causing everything to go wrong, and it either crashed onto on the Earth, it crashed into Mars, or it flew off into space, never to be seen again. This mistake cost the US $327 million, which is $639 million in today money. Well, today being more because it's been more time since December 2024. The takeaway there is that as silly as it seems, not having a unit or having the wrong unit can be crippling. How can we follow instructions if you don't have instructions, if you don't have the right measurements? We also need units to be understood by all parties. Here you can see the guys that made the thrusters and the software that used these were 2 different companies. So because there was no communication, there was a serious and severe failure. So overall, units are words that help us describe the world to each other. This is important because chemistry is communication of the world around us, so we need to be accurate. Our job as chemists is to accurately and succinctly communicate the world to each other. So all that comes together, and scientists said we need one system to describe the world so that we can more accurately and succinctly report our measurements. What do they come up with? The metric system. So what is the metric system? The metric system is the world's most used system of communication for scientists. It's intended to have the least amount of miscommunication between everyone because everyone agrees and all the units are defined. It was invented by the French in 1799 to unify measurements in an increasingly connected world. If you've taken a history class, 1799, that was the era of colonialism and the beginning of globalization. So previous situations, such as a Chinese guy working with a French guy, were not as common as they were in this time. So there had to be new ways to communicate with each other, and that's where the metric systems had its genesis. So how does it work? So the metric system works by having predefined units of measurement defined in relation to nature that we can compare to. This is called a standard. There is one definition of each of these, and there are 7 total. So for example, here you have the original standard for a gram, which is a measurement of mass. This, up until 2019, was what all grams are measured. If you told me I have 1 gram, what you were telling me is that somewhere out there, there was a chunk of metal that had the exact same mass as what you were giving me. There are a total of 7 base units in the metric system, which we'll cover in the next slides. The base units. So they are referred to as the base units because they measure the 7 most fundamental measurements of nature, as in the 7 most basic things. Each unit has its own symbol for written shorthand so that you can write it and people will understand. And here they are. What you have here are the 7 units, which are meter, kilogram, second, Kelvin, mole, candela, and ampere. They all have symbols, so you have M, kg, S, capital K, mole, CD, amp. And they measure all these things, which we will go into individual units in detail. I want to point out that kilogram has an asterisk next to it, which we will get to when we cover kilograms. So to start, we'll look at meter. Meter is nowadays defined by the distance that light travels in a certain time. It's very small. However, back in the day, there was literally a meter stick, which was a stick as long as a meter that you could compare to. If you've ever used a meter ruler has to be the same length as this stick. This definition has been phased out for nerd reasons. Don't worry about it. Just know that a meter has a measure that it compares to. A kilogram. So a kilogram is formally defined by the metric gram, which was this. It uses kilo as a prefix, so it will cover what a prefix is, but I've been talking about the metric gram, and we're talking about the basic being the kilogram. This is actually a historical quirk and not something measurable. So the reason for this is the gram would be the base unit, except in the 1790s when the metric system was created, people didn't really buy grams. When you were doing business, you would be asking for a kilogram of something, right? You would be asking for a kilogram of wheat, a kilogram of beef. Ordering a gram of beef, that's not very helpful, kind of difficult to do. So people worked in bigger numbers, and because of that historical quirk, we still use kilograms. Second. So the second is defined by its original definition, which is we took the day, divided that by 24 to get the hours, divided each hour by 60 to divide it into minutes, and divided each minute into 60 to get to seconds. Now it's defined by Nerd Talk, which is here. You can read it on your own time. But ultimately, a second is a unit of time, which can be used. If you say you have a kilosecond, that means you have 1,000 seconds. Kelvin. Kelvin is a measurement of temperature the same way that Fahrenheit is. You in your daily life might know that today, May 12th, the temperature was about 105 degrees Fahrenheit. That means that there are 105 units of temperature that we got up. The big problem with that is that the 105 is not measuring exactly 0 degrees. So if you get all the way to 0 Fahrenheit, that's not the absolute 0 of the universe. Kelvin fixes that. Kelvin starts at 0 of the universe and goes up. So if you were to try to describe 0 Kelvin in Fahrenheit, you would say negative 459.67 degrees Fahrenheit. Kelvins are the same size as a Celsius, and they are defined using energy in a way outside the scope of this class. Moles. Moles measure the amount of a substance. A mole is the same way that a dozen is 12. A mole is 6.022 times 10 to the 23rd. We'll cover that later. But it's literally counting the amount of atoms in a thing, which is another thing we'll cover later. But we will cover it. Candela. Candela measures the light emitted by an object. So if you look back there, I have 2 lights. I can measure the brightness of them using candela. The definition is even nerdier and more complicated than everything else before. Again, I will not be reading it because, again, we don't need to. For this class, we are not concerned with the definition. I just need you to understand that when I'm talking about candela, I'm measuring luminous intensity. Fun fact, scientists are constantly improving. All of these units were redefined in 2019 to be based on universal constants. This fundamentally does not change you or my experience with the metric system, but it does help us to understand that in our constant quest as humanity to try to communicate accurately and honestly with each other, we will continue to make improvements so that we can get rid of any inconsistencies caused by language. Okay, so what do we do with these base units? So if you try to communicate with just them, you're going to run into the limitation that your numbers can get big and small and not be very well defined unless you add more to them. So for example, in this case, Dr. Ion is telling Dr. Isotope that he had to travel 136,517 meters last week to go to a concert. What does that even mean, right? To me, I know that it's 136 kilometers, which is approximately 100 miles. So he might have driven from Phoenix to Tucson, for example. But Dr. Isotope might think, I understand what he means, but he said it really inconveniently. That is just a big number to be using. So to handle this, we can use what are called prefixes and move on to our next section. So prefixes in scientific communication. A prefix is an additional word that goes before a unit to indicate its size. So essentially what you're saying is if I use gram, I can describe really big numbers using gram and really little numbers using gram. Here is an example using meters. This is in your book. It is in your reading. This is an example of different scales of measurement. You can see here, M, you can measure a man using M, right? 1 meter, 1.75 meters is about the average for men around the world, something like that. Kilometers is bigger, right? It's about the size of a city. Keep going up. Megameters is in terms of the size of the Earth. Gigameters is the distance between the Earth and the Sun. There's more examples in the next slide, so I'll move to that now. So there are different prefixes that all have defined meanings. So for example, giga means that you take that measurement and you multiply it by 1 trillion. So 1 times 1 million and 1,000. So distance between the sun and the earth, between the sun and Saturn would be 0.886 gigameters. So if I told you gigameter, it would mean something really big. If you think about kilometers, when you come to this class, the distance between your house and Paradise Valley Community College could be hopefully less than 25 kilometers, but you would understand how big of a distance that is because you have to drive it. If you've ever heard the word microscopic used to describe small things, the width of a bacteria cell is microscopic. It's a micrometer. That said, you might hear atoms described as microscopic, which frustrates me because they're even smaller. You actually would want to describe them as nanoscopic, which means if you take a meter divided by 1 trillion, that's how big a thing is. We could talk about it more in class and I can give you better examples, but I want you to understand that you can put a free prefix before any of the base units. So you can have a kilo candela, you can have a gigasecond, you can have a micro Kelvin. All of these just change the size of whatever you're describing. I want to show you how much more difficult this would be if we were to use imperial, which is the system that we use. In imperial, 1 inch is about 2.54 centimeters. You take an inch, multiply by 12, you get a foot. You get a foot, multiply by 3, you get a yard. You get a yard, multiply by 1760, you get a mile. This is not very helpful to describe big or little numbers. If you try to describe an inch as a nanomile, that would be silly, right? And that would also be very incorrect. So prefixes give us a quick way to explain size without losing our minds. So you can always just throw the symbol before your word. So for example, if you wanted to say milli, you would put little m, mega, big M. The one specifically that I want to point out to is micro. Micro uses this symbol, which is mu. Mu is the Greek letter for M. We ran out of other M's, so we had to use another one. You also might see U instead because it's easier. Think about on your computer does not have a mu key, but it does have a U key. So a lot of scientists report things back in UM, and that's defined as microns. And a micron is a micrometer. That's just another word. So how, bring that all together and we can describe size, right? We go back up here and we can say kilometer, micrometer, etc. The big limitation here is that we are only able to measure one thing. Those are the basics, right? So how do we discuss more complicated measurements? What if I want to tell you about the speed, or I wanted to talk to you about area? What could we do here? The metric system is defined as base units. Base as in basic, as in we can do more with them. We can build with them. Here is one example, which comes from 2001. Arizona Diamondbacks pitcher Randy Johnson made history by blowing up a bird with his fastball. The odds of this happening are crazy, but essentially he pitched and a bird flew down, and his pitch was moving so fast that this bird exploded. So sources estimate Johnson's throwing speed to be 45 meters per second, which, what does that mean? That means that in the time that the ball flew from here to here, if it traveled for 1 second, it would have traveled exactly 45 meters at the same time. So 45 meters per second means that the ball would travel 45 meters in the same amount of 1 second, which you can then write as 45 meters per second. Similarly, volume is defined using length. If you've ever seen the formula for a cube is length times width times height. So length times width times height, or length, width, height. This literally means a meter cubed, or meter 3, which is equal to meter times meter times meter, which is the formula that you had before. So if I told you a meter cubed, you could be able to conceptualize volume. This is something that we'll also cover more of in class, but I want you to understand where this definition begins. There are other examples that we can do, which again, we will save for in class. There are more of them out there. Again, I'm repeating myself. We will learn more in class. Thank you. So bring all that together. What's important about this topic? So throughout today, we have established a communication framework for future classes and labs. So we have agreed that science needs very strong communication, and in order to do so, we are using the metric system. Why? Because the metric system allows us to have one set language that transcends cultures, peoples, and times, so that our measurements can always be understood and read by other people. Remember, the key point of the metric system is so that all scientists can help each other with one shared language. So, go back to the topics of this lecture. We talked about units, we talked about the metric system, we talked about the 7 base units of the metric system, how to use prefixes, and combining units to describe more complicated systems. We can talk about this more in class. Please write down any questions you may have. Thank you for your time. See you on the next one.